Hello, everyone. I hope that you are adjusting well to all the changes that have happened in the last week. There have been so many of them in such a short period of time. And I know that's probably stressful for a lot of people. It's not easy to make such big changes and still have to finish all your courses. So I hope that you're adjusting, and if not, I hope you adjust soon. In this video, I just wanted to go over some of the questions from March 18th to give some clarity to some of the answers I gave you on Blackboard. If you check your answers, I responded to some of you if I thought you needed some feedback, but I'm going to add more here. So the second question I want to go over, what mistake did Dr. David Berliner make in his testimony in Vergara v. California, and why should we not make the same mistake? So he actually just made up data in his testimony, and the judge used that information to make a decision in his case. And one of the reasons why we shouldn't make things up is that it has real consequences. People use information that we give them to make choices, and if we give them bad information, that they could make a bad choice based off of that, and people can be harmed. And I think we are having this debate right now in current events about how the government communicated to us about the coronavirus in the first couple of weeks it came to the United States, and whether or not they were honest with us about how bad it could get. And so, if what more did they know? Should they have warned us? Should we have been making different or taking precautionary measures sooner, right? So I think perhaps when this is all over, we're going to be having those conversations a lot. Because maybe if they did know something, we could have prevented some deaths if we were making changes sooner. That's not to say I think that's what happened. It's just a possibility. And I'm actually going to send you a link to a video about the 1918 Spanish flu epidemic or pandemic that talks about how the government prevented newspapers from telling the public about it because we were at war and they didn't want to hurt our efforts in the war. And there's a historian in that video that talks about how that led people in cities like Philadelphia to not take any precautionary measures, and thousands of people died because of it. You don't have to watch the video, but if you want to, it's only 6 minutes long and it's really interesting. Okay, so question 3. How did the authors manipulate the data in figures 6.3 to 6.8? So in figure 6.3, this is the actual data the way it should be presented. So the authors wanted to know how hours of exercise per week influence mortality risk. And based on this data, it demonstrates that the more you exercise, the more reduction in mortality risk goes up. But then the authors started manipulating the data. So one of the first things they did was, in this chart here, they have a category for 0, and if you exercise 0 hours per week, you have no reduction in mortality risk. But what they did in this chart was they put 0 to 7.5 in the same category, and so it looks like exercising up to 7.5 hours per week has no impact on your mortality risk, even though we know that that's not true up here. In this chart here, what they did was they took out everything above here, because as you can see, there's an increased benefit here, but then it goes down. So they took that out here so that you can't see that at some point exercising too much is actually bad for you. In this particular chart, they increased the range of the y-axis. If you look at the original chart, it really only goes up to 45, and it really only should go up to 45. By putting it up to 95, it makes the bars look shorter, and so it makes it look like there's less of an impact here. And we can actually do this in Excel. And as many of you know, when you make those bar graphs in Excel, you really have to open them up because the bars are really small at first, and it shrinks the size of the bars and it makes them look less significant. So the takeaway message from here is, the y-axis should go from the minimum to the maximum, or at least from 0 to the maximum. It should not go up to above that. And in this chart here, they flipped the axis, so the x-axis should be here, but then they put it over here. And so unless you look at the numbers, because now it's decreasing instead of increasing, it changes how you think the data looks, so or the conclusions you make. So this actually looks like as hours of exercise per week go up, there's a slight impact on mortality or reducing mortality, but then it quickly goes down. So this makes it look like exercise doesn't really affect mortality risk, or it doesn't really have positive effects on mortality risk. And then this last one here is really interesting. They took the x-axis, which was up here with the bars going up, and they just flipped them upside down. And so it actually looks like that as hours of exercise go up, the mortality risk is going down when it's actually, or reduction in mortality is going down when it's actually going up, right? So this should be a positive relationship, but it looks negative because of the way the axis is flipped upside down. So the point of this question was to show you, and this is especially useful for your final paper, that you should be really careful about how you're constructing your graphs, and this goes into the next question. On the x-axis, you should make sure that you have the range from the minimum to the maximum should be the minimum of your variable to the maximum of your variable. Don't cut out numbers to make the graph look the way you want it to. So it should go minimum to maximum. And then on the y-axis, it should go from 0% or the lowest percent in the data, but 0 is probably the best, to the highest percentage bar. Okay, not much further up. So minimum to maximum, and then in the variable, and then 0 to the highest percentage bar. And also make sure to expand the graph so that it's clear what the bars look like. Don't make, when you're putting it on the PowerPoint, don't make it super small so the bars look small. Okay. Question 7. How does a presenter's clothing choices, like a lab coat, influence whether listeners accept their results? And I think we all, experience this when we see somebody we think is an expert, or they're very eloquent with the way they talk, or they sound authoritative, like perhaps, this is something that I've noticed in academia, is like a tall man with a deep voice sounds more authoritative than a short woman with a very high-pitched voice. And what happens is that we think these people, we get these, something happens in our brain where we think, oh yeah, that person must know what they're talking about because they sound like they're an expert, or they look like they're an expert. The problem with this is that just because somebody's an expert doesn't mean they're right. Okay, so there's something that the book doesn't talk about, but I want to talk to you about. It's called an appeal to authority. It's a logical fallacy. So if you've ever gotten to an argument with somebody and you're presenting them with information from, let's say, a scientific study, and they say to you, well, that can't possibly be true, and then you could say something like, well, an expert said it, so it must be true. Well, that's not true, right? So just because somebody's an expert doesn't mean their arguments are right. They could have something, there could be a logical flaw in their study, in their reasoning. They could be using bad evidence. So really, when we see somebody we think looks like an expert, we shouldn't assume what they're saying is true. What we should be doing is looking at their arguments, looking at their reasoning, looking at their evidence, and basing our conclusions about whether we should support or believe their conclusions based off of that alone. We should not just accept their conclusions because they're an expert. And I think the opposite is also true. If you see somebody that you don't think is an expert, don't just dismiss what they're saying because they don't look or sound like an expert. Think about what they're saying. Think about what evidence they're presenting. That's what really matters in the end. And then here, question 8. What can we learn from John Oliver's piece on climate change about how we should weigh scientific evidence with conflicting results? What John Oliver was trying to show is that there's overwhelming support that climate change is happening, that humans are doing it, that it's harmful, that it could have negative consequences. But there are some people who just don't want to believe that, and they'll find like the small percentage of studies that contradict the consensus, right? So there's always going to be a handful of studies that contradict the consensus. And this is just because of how statistics work. You're wrong. Remember when we talked about in class, you're going to be wrong about 5% of the time, right? Like, just based on the way data analysis works, 5% of the time we're going to be wrong, and so we're going to get studies that are wrong. And so so what he's trying to show is like there are going to be people who are going to latch on to those wrong studies just so that it conforms to the way they think the world works. And we got to step back from that, and we have to say, okay, recognize, like, is this what I want to believe, or is this truly what reality is, right? So try to look for consensus first, right? If the evidence contradicts if the overwhelming evidence contradicts your belief, put more weight on that, okay? Even if it goes against how you think the world works, it's better for you to, as a scientist, to accept reality, because that means that you can make better choices, better public policy choices, than it is for you to, latch on to outlier studies and look for any evidence to support your argument, just because it makes you feel good, right? We like to feel like we're right? So just try to avoid cherry picking evidence or looking for things that just support the way we think the world works. There's a movement called the Flat Earth movement, or Flat Earthers movement. I don't know if you've heard of it, but there are people out there who think the Earth is flat, and you can look up videos on this on YouTube. Like, they'll do experiments to say this experiment's going to show that the Earth is flat, and clearly the results of the experiment show that the Earth isn't flat, and yet after they do that, they say, well, I guess this experiment doesn't show it, but we'll find something else that does. So even in the face of evidence, they can't accept reality, and that's just not good. So as a good scientist, I encourage you to sort of detach yourself from your, from the way you think the world really works, and try to think more about, or put more value on what the data are telling you. So anyways, like I said, I hope you're having you're transitioning well to this online format. After spring break, I'm going to have all the next questions up for the next discussion, and I'm actually going to organize it just a little bit differently on Blackboard, just to make it more organized in the discussion boards, so that everybody in their groups are answering in the same part of the discussion board as opposed to different parts. If you have any questions, feel free to email me. Otherwise, I hope you enjoy your spring break. You all definitely need one.